This is part 2 of our introduction to hypothesis testing. When you're testing a claim about a parameter, you start with 2 contrasting hypotheses, which we call the null hypothesis and the alternative hypothesis. We looked at some examples of those. Then you collect some sample data. You use that sample data to compute a probability, and we haven't talked about how to get this probability yet. That will be one of the points of this video. But we compute the probability that a randomly generated sample would provide observations as extreme as what we actually saw. This is part of that rare event rule that we discussed in the last video. Based on that probability, we make a decision about the validity of one of the claims, and then I'm going to ask you guys to write me a conclusion. What can we infer from the decision that we made? We'll talk about those conclusions in this video as well. Quick reminder of the 2 decisions. After we compute that probability, we'll decide either to reject the null hypothesis or fail to reject the null hypothesis. When we reject the null hypothesis, we're saying that the sample data provides strong evidence suggesting that the null hypothesis is false. We're pretty sure that the null hypothesis is false, and we're going to go out on a limb and reject it. Remember that this is done on the basis of probability, so we're not sure that it's false. We're just saying that the evidence leads us to believe that it's false. On the other side, sometimes the evidence isn't that strong, and so we fail to reject the null hypothesis. When we fail to reject the null hypothesis, we're saying that the data we gathered does not provide enough evidence to be comfortable concluding that the null hypothesis is false. The evidence that we gathered kind of leans against the null hypothesis, but it's not strong enough for us to be sure that the null hypothesis is false. So we concede and we say, okay, we're not really sure that it's false. Now again, this decision is made on the basis of probability. So it's possible that we've been misled by the sample data. When we gather that sample might not be representative of the population. Even if you do everything correctly, you gather a simple random sample from the entire population. You do all of your calculations correctly, but the sample that you gathered is just strange for that population. It's just not representative. That can happen when you use a random sample. You might randomly get elements that are not representative of the entire population. Because of that, sometimes the decision is wrong and you've made what we call an error. This doesn't mean human error. It's an error that happens because you were misled by the sample data. And of course, because you're trapped in math nerd land, we have names for the 2 errors. We have a type 1 error and a type 2 error. A type 1 error occurs if we reject a true null hypothesis. Let me explain why this is an error. When you reject the null hypothesis, you're saying that you're pretty sure that the null hypothesis is false. So if the null hypothesis is actually true and you reject it, that's an error. Rejecting a true hypothesis would be an error, a mistake. Again, not human error. You would reject a true null hypothesis because the data that you gathered made you believe that the null hypothesis was false, and it turns out that it was actually true. Don't think error like a mistake made by the person conducting the study. It's an error because you were misled by the data that you gathered. Everything you did was statistically and mathematically solid, but the data wasn't representative of the population, so you make the wrong decision and you reject even though you shouldn't have. On the flip side, a type 2 error occurs if we fail to reject a false null hypothesis. When you fail to reject the null hypothesis, you're saying that the data doesn't provide enough evidence for you to be comfortable saying that the null hypothesis is false. So when you fail to reject, you're kind of saying, well, maybe the null hypothesis is true, but it isn't. It was false. That would be an error. Again, that error is made because the sample misled you. If the null hypothesis is false, then most samples would lead you to reject it. But the sample that you gathered completely by chance, not because you did something wrong, but just based on probability, the sample that you gathered was not representative of the population, and therefore you weren't able to reject. We use the severity of the type 1 and type 2 errors to guide our decision. If a type 1 error is really, really bad, then we have to be very, very sure that the null hypothesis is false if we're going to reject. We'll want to avoid making a type 1 error. And similarly, if the type 2 error is bad, we want to avoid making that one. So we'll be wary to fail to reject. Now, how do you determine the severity of a type 1 and type 2 error? Well, it depends on the scenario that you're in. It's not always the case that one is worse than the other. It depends. So here's an example. This is a classic example. Something like this is in every textbook, whether it's about rock climbing or parachutes or something. You'll find a problem like this in every book. So you jump out of an airplane with a parachute on your back. You're going skydiving and you've got a parachute on your back, but before you jump, you kind of consider whether the two possibilities. So I've turned these into hypotheses. The null hypothesis is the claim that the parachute will open, and the alternative hypothesis is the claim that the parachute will not open. So a type 1 error occurs if you reject a true null hypothesis. A type 1 error occurs when the null hypothesis is true, but you're led to believe that it's false. So in this example, the null hypothesis is the claim that the parachute will open. In a type 1 error, you think that's false, but it's actually true. So the type 1 error would be that you think the parachute won't open, but it does. You thought the null hypothesis was false, but it's actually true, and the parachute really does open. Let's explain why this is an error. Suppose you decide not to use this parachute because you don't think it will open, but somebody else uses it, and when they jump out of the plane, it does open. That's a mistake. You just gave away a parachute that would have opened for you. That's an error. Let's look at the type 2 error. A type 2 error occurs if we fail to reject a false null hypothesis. So the null hypothesis is the claim that the parachute will open, and we don't reject that claim. So we kind of accept the claim and we think that the parachute will open, but it turns out that that's false. So you think the parachute will open, but it doesn't. That's a very bad error. And in this example, you can see the type 2 error is much worse than the type 1 error. Now, don't read into that. The type 2 error isn't always the worst of the two errors. All I have to do is flip-flop my two hypotheses, and then the type 1 error will be the worst of the two. So sometimes the type 1 error is worse, and sometimes the type 2 error is worse. And we use the severity of the errors to help us make our decision. That's part of the process. If the type 1 error is really bad, then we try to reduce the probability that that happens. And if the type 2 error is really bad, then we try to reduce the probability that that happens. And so here we go, more notation. We give symbols to these probabilities. The probability of a type 1 error is alpha. This is the first letter of the Greek alphabet. Alpha kind of looks like 3/4 of an infinity, or it kind of looks like, you know, when you were in 3rd grade and you would draw a fish, you just don't draw the eye on the smiley face. The probability of a type 2 error is beta, the second letter of the Greek alphabet. I have to bring this up every time I talk about alpha and beta. Our word alphabet comes from alpha and beta. We're going to use alpha in our decision-making process, so we're going to give that an extra name. Alpha is called the level of significance, or sometimes the significance level. And we take these probabilities into account when we make our decision. If a type 1 error is really, really bad, then we want alpha to be small. And if a type 2 error is really, really bad, then we want beta to be small. And of course, I know what you're thinking, well, why not just make both of them small? Well, here's the thing. If you make alpha smaller to avoid making type 1 errors, then beta gets bigger, all other things equal. Avoiding type 1 errors leads you to make more type 2 errors, and trying to avoid type 2 errors makes you make more type 1 errors. If beta gets small, then alpha gets bigger. The only way to reduce them both is to increase your sample size. The larger your sample size, the smaller these probabilities get. But you can't just make both of them arbitrarily small, because they kind of teeter-totter. When one gets smaller, the other one gets bigger. So we just kind of choose the probability of a type 1 error and let that affect the probability of a type 2 error. And when we choose that value of alpha, we do it based on the severity of a type 1 error. If a type 1 error is really bad, then we would want alpha to be small. A common small value of alpha is 1%, 0.01. But if you have a really, really severe type 1 error, you might take it even smaller. But keep in mind, if you make alpha really small, then that increases the probability of a type 2 error, and you'll make type 2 errors relatively often. If the type 2 error is really, really bad, like in our parachute example, then you let alpha get bigger, and a big value of alpha would be like 10%. You're making type 1 errors 10% of the time, or a better way to say that would be 10% of the samples that you gather would lead to a type 1 error. Making incorrect decisions 10% of the time in this direction sounds bad, but we do that to avoid making errors in the other direction when the type 2 error is worse. The most common value of alpha is 5%, 0.05. When it's hard to judge if a type 1 error would be worse than a type 2 error or vice versa, then we set alpha to 5%, 0.05. Now let me interject here and say that in a textbook problem, on a quiz or on an exam, you will not have to choose the value of alpha. It's given to you. So determining how severe a type 1 or type 2 error is isn't something you're going to have to do as part of this process. You're going to be fed a value of alpha that you'll just use as part of the process. Okay, so we use these probabilities to help us make the decision. Let's go back through our process. We make that decision based on a probability that we've calculated. And while I might be jumping ahead here, let me just note really quickly that this probability is going to get compared to alpha. That's why I was talking about it. That wasn't just for trivia. We're going to need it. But we have to compute this probability. We compute the probability that a randomly generated sample would provide observations as extreme as what was actually witnessed. We call that probability the p-value. The p-value is the probability that the statistic could be at least as extreme as the observed value under the assumption that the null hypothesis is true. The probability that we calculate is the probability that we could have witnessed something at least as weird as what we saw if the null hypothesis was true. We're assuming that the null hypothesis is true. If our p-value is small, then it's unlikely that the null hypothesis is true and we're going to reject it. If the p-value isn't really small, well then the null hypothesis is believable and we fail to reject it. That's the basic idea. Now that begs the question, how do you determine what's small and what's not small? We'll get to that. But first, let me show you really quickly how we would even calculate a p-value. So I've got a scenario here based on a real-life study that gets repeated a lot. It's commonly believed that a healthy body temperature is 98.6 degrees Fahrenheit. Various studies have been published testing whether or not that's true, and so I've got these contrasting claims here. The null hypothesis is the claim that's usually made, which is that the mean healthy body temperature is 98.6 degrees Fahrenheit. And the alternative claim here is that the mean is less than 98.6 degrees Fahrenheit, that the average healthy body temperature is actually below 98.6 degrees Fahrenheit. So the people who did this gathered a sample of 36 individuals who were healthy. They got their body temperature, which is 98.2 degrees Fahrenheit. And they're assuming to know the population standard deviation is 1.6. So just to lay out the scenario, 98.2 is obviously smaller than 98.6, but they only took a sample of 36 individuals. Is that evidence statistically strong enough to be sure that the mean body temperature of all healthy people is below 98.6 degrees Fahrenheit? Well, how would you determine that? You would calculate this probability and make a decision. And the way that we would calculate this probability is to use our knowledge of sampling distributions. We know that because the sample size is 36 that we could assume normality here. And here's the kicker. We're going to assume that the null hypothesis is true. When you calculate this probability, you assume that the null hypothesis is true, and we're going to assume that the number in the middle of this distribution is 98.6, that the mean of the means is 98.6. Remember that the mean of the means is equal to the mean of the population. So we pretend like the null hypothesis is true, and we calculate the probability that the statistic could be at least as extreme as the one that we saw. So we saw a sample mean of 98.2. So we would go over to 98.2, and we would measure the probability that it's at least that extreme. Now, what do we mean by extreme? We mean as extreme in the direction of the alternative hypothesis. The alternative hypothesis is the claim that it's less than 98.6, and so we go less than that. And that area would be our p-value. Where does the standard deviation come in? Well, we need sigma sub x bar, and sigma sub x bar is the standard deviation of the population divided by the square root of the sample size. If we know the population standard deviation and we have a sample size of at least 30, then we know that the sample means follow a normal distribution. And so we could find this p-value using normal CDF. It turns out that we won't have to do that because there's going to be a calculator function that will do it for us. But this is something that we could already do. We already know how to do this even without learning any new calculator functions. I'm not actually going to drag you through it, but that's how you would calculate a p-value. You pretend like the null hypothesis is true, so you accept that mean as fact, and then you say, what is the likelihood that we could have gotten a sample mean this small or smaller, because the direction of the alternative hypothesis was less than, under that assumption? That's the p-value. If this had been a greater than, then we would have shaded to the right. But it would be silly to guess that the mean is greater than 98.6 because our sample data doesn't point in that direction. So our p-value would have been really, really big. So if the p-value is small, then the null hypothesis is not that believable. We've assumed that the null hypothesis was true, and then saying what we witnessed has a very small probability. So if the p-value is small, then we reject the null hypothesis. If the p-value isn't small, then we fail to reject the null hypothesis. And this begs the question, how do you determine what's small enough to reject? This is where alpha comes back in. Remember that alpha was the probability of making a type 1 error. And that probability is based on the severity of a type 1 error. So if alpha is small, we're afraid of making type 1 errors, and we need a very small p-value. So we'll just say, if the p-value is less than or equal to alpha, we'll reject the null hypothesis. Alpha is like our danger level for making a type 1 error. If our p-value is even smaller than that, then we feel safe rejecting the null hypothesis. If the p-value is bigger than that alpha, then we'll fail to reject the null hypothesis. We'll risk making a type 2 error instead. That's how this all comes together. I like to explain the p-value in the following way, but always with this warning. What I'm about to say isn't actually true, and if you say it to a real stats person, they'll probably want to fight you or fight me because I'm the one who told you to think of it this way. So while what I'm about to say is false, I always encourage students to think of it this way. The p-value is like a measure of how believable the null hypothesis is. If the p-value is small, then the null hypothesis is not very believable and we reject it. And how do we determine what's small? Smaller than alpha is small enough to reject. If a type 1 error is really bad, then we're afraid to reject the null hypothesis when it's actually true, so alpha will be small. The p-value will have to be even smaller than that in order for us to risk making that type 1 error. That's how we make the decision. The last thing I want you to do is write a conclusion. So how do we write that conclusion? Well, if we reject the null hypothesis and say that we're pretty sure that it's false, then we're going to conclude that we're pretty sure that the alternative hypothesis is true. If we reject the null hypothesis, then we conclude that there is enough evidence to support the claim made by the alternative hypothesis. A lot of times the null hypothesis is like a historical value of the parameter. And for some reason we believe that that historical value has changed, and that's the claim made by the alternative hypothesis, that it's now bigger than what it used to be, or smaller than what it used to be, or maybe just different than what it used to be. So if we reject the null hypothesis, we're going to replace that claim with the alternative hypothesis and say that we believe the alternative hypothesis is the truth. On the other hand, if we fail to reject the null hypothesis, then we conclude that there's not enough evidence to support the claim made by the alternative hypothesis. This is important. If we fail to reject the null hypothesis, we are not saying that the null hypothesis is true. We're just saying there wasn't enough evidence to suggest that it was false. Those are two different things. Just because you can't prove that something's false doesn't mean that it is true or that you even have evidence to suggest that it's true. So we have to be careful with our wording there. We would never support the null hypothesis. We either reject it or we fail to reject it. Similarly, we either support the alternative hypothesis or we conclude that we could not support the alternative hypothesis. I think some of those nuances will be clearer when we look at actual examples. For now, we're looking at this abstractly, and I know a lot of this might be swimming around in your head. I encourage you to come back to this video and the previous video after you've seen us demonstrate some examples in future lectures. I think a lot of these ideas will make a lot more sense when you've got something to tie it to, when you've got a specific example. So after you've seen examples of the 3 calculator functions we're going to learn, revisit these lectures and see if the pieces make more sense. Of course, if you have any immediate questions, please contact me. I'll try to clear things up as much as I can.